Hey, welcome back, you crazy cats. Today we're going to talk about what you're going to learn. You're going to learn about what is a normal, what is friction, and to apply the equation for friction. The normal force. This is the force that is acting perpendicular to the contact point. It points away from the surface. Examples. Well, here we have a normal. All right, it's going to be pointing up. It is perpendicular to the normal, or to the surface. That's usually pretty easy for students to understand. Over here, though, we have a surface that is slanted. So our normal would be acting perpendicular to that surface still. The weight, then, would be acting still straight down. And that right there, then, that would be our weight. All right, notice it's still acting straight down towards the earth, or perpendicular to the earth's surface, not perpendicular to the surface that you could be on. So you could be on a ramp, and the normal would be pointing perpendicular to the ramp, but your weight would still be pointing perpendicular to the earth. Friction. Well, let's talk about friction here a little bit, then we'll come back to the normal. The force of friction always opposes the direction of motion, or the direction the motion would be in the absence of friction. Depending on the circumstances, friction may be desirable or undesirable. If you want to be able to move, friction is a desirable force. As you can see down here, that it says the force exerted on the ground by the foot. All right, so friction then is how much force, you're pushing backwards, and the frictional force is exerted on the foot by the ground. It's friction that actually pushes you forward. Sometimes that's hard for students to understand, but friction is always going to act in the opposite direction of the motion. So think about this. If the foot were to slide, which way it would go? It would be sliding backwards. So which way would friction be acting? Well, it would be acting in the forward direction. It's going to act in the opposite direction of the motion. Types of friction. Static friction. This is when frictional force is large enough to prevent motion. So when you push off the ground, you have static motion. All right. Kinetic friction, when two surfaces are sliding along each other. This could be like when a car hits the brakes and you hear that screeching sound. All right. The car is still sliding, all right, to a stop. There is friction, but the two surfaces now are sliding next to each other. It's not stopped. The car doesn't stop immediately. Rolling friction, when an object is rolling without slipping. Again, we're talking about it could be the tire on the road. You have that rolling friction. All right, so we observed that the frictional force is proportional to the normal force. For static friction, we have that the static friction is less than or equal to the coefficient of friction for static friction times the normal. This constant, this is mu of static friction. This is the coefficient of static friction. It's called the coefficient of static friction. Sometimes it's also called mu. The static frictional force may not have its maximum value. Its value is such that the object does not move and depends on the physical circumstances. So when you can have that maximum static friction, all right, then we can say that's equal to, and we have the coefficient of static friction times the normal. For kinetic friction, it's the exact same equation, except the only thing it would change would be the coefficient for kinetic friction. All right. The constant mu k is called the coefficient of kinetic friction, is usually smaller than the coefficient of static friction. Think about it. There's a reason why cars have anti-lock brakes. They don't want your tires to be sliding. They want your tires to have rolling friction so that you have static friction. It's going to allow you to stop much faster because the coefficient of static friction is larger. This figure illustrates what happens as the applied force increases. First, the static frictional force increases, then the kinetic frictional force takes over as the object begins to move. So on here we have the person is pushing, but the static friction is equal to or greater than what the force they're pushing. So what you see here then is that the force starts to increase. And at some point, you'll see right about here, maybe the second person starts to push as well. And what happens is the filing cabinet starts to slide. Well, once you get it sliding, all right, once you get it to go past the maximum static frictional force, what will happen is you'll see that the amount of force it takes will drop. And that's what's happening right here. The amount of force is dropping. It's easier to get this cart, or to get this filing cabinet to keep moving once you get it moving. So what we see here then is they have small force, that's probably maybe somewhere right in here, and then they meet that maximum force right here, because you notice that the static frictional force has had its max, and then they get it moving. So the kinetic frictional force here is smaller. The magnitude of the vector is smaller than it is the maximum static frictional force. So then we have this constant kinetic frictional force. Alright, so here we have a chart of the coefficient of friction dependent on both materials involved. Aluminum on aluminum. Well, notice that aluminum on aluminum has a fairly high static frictional force of 1.9. The kinetic frictional force, 1.4. Glass on glass, you have two very slippery surfaces, 0.94 and 0.35. Rubber on concrete, notice that this dry static frictional force is 1.2. Wet, it drops down to 0.8. And then for kinetic, if you're moving, dry is 0.85, and if it's wet, it's 0.6. This is interesting. I'd write these down, because we'll do some examples with this. And there's other ones here as well, but we'll talk about those as needed. Friction. This form for the frictional force is an approximation. The actual phenomenon is very complicated. The coefficient of friction may vary somewhat with speed. There may be some dependence on the surface area of the objects. Also remember that these equations are for the magnitude of the frictional force. It is always perpendicular to the normal force. And why. All right, so real quickly, why don't you see if you can answer why that frictional force is always perpendicular to the normal force. Air resistance is another form of friction. It depends on an object's shape and size as well as its speed. For an object in free fall, as the force of air resistance increases with speed, it eventually equals the downward force of gravity. At that point, there is no net force on the object, and it falls with a constant velocity called the terminal velocity. So what we're talking about here is some object, and as it falls faster and faster and faster, this upwards vector, this frictional force, increases. And at some point, it's going to equal the object's weight, or the pull of gravity on it. Well, what happens when these two forces become equal and cancel each other out? Well, that means there's no net force anymore. So it'll no longer accelerate. And that's when we call that terminal velocity. Okay, so what I've done here to start off with this problem here to save us some time is I've read through the problem. It tells us that there's a 100 kilogram box sitting on a flat surface and it requires a force of 500 newtons to overcome static friction. So I've made a list of the given information. Now I'm going to start writing my equation. Static frictional force is equal to mu of static friction times the n. Well, remember, the normal is mass times gravity. So in this case, we can say that 500 equals mu. N is m times g, so let's find n real quickly here. That's 100 times 9.8. N equals 980. Mu then is going to be equal to 0.5. Notice that the normal is mass times gravity, or a force. That would be newtons. Force is in newtons. When we take 500 newtons and divide it by 980 newtons, we get no units for mu. Okay, so I've given me a head start here. I've made a picture to represent this. We've got this sled. This is our sled, and it's got an engine that's pushing forward at 2,000 newtons. We have this frictional force that's pulling back on it. It's opposing that object's. Its mass is 750 kilograms. It says, find the acceleration of the sled. Well, the sum of the forces is equal to the frictional force plus the force of the engine. In this case, then I can say that MA is equal to the frictional force, which is mu times N, plus the force of the engine, which I'm just going to go ahead and put 2,000 in there. Now, I'm going to put a negative here because the force of friction in this case, I've decided to make 2,000 positive, so the force of friction needs to be negative. The mass in this case, then I'm going to do the normal, it's mass times gravity. So I've plugged in some numbers we know here. 750A equals 1470, negative 1470, plus 2,000. 750A equals, when we add these together, we're going to get 530. The acceleration is going to be a very small number, which turns out to be 0.71 meters per second squared. Well, hey, hopefully that helped you understand a little bit about friction. I'll catch you on the flip side.